All right, so now let's apply this to this idea of conservation of momentum and these 1D collisions. So collisions, most common scenario where we're going to use that conservation of momentum, because when objects collide, the mechanical energy may not be conserved. And so and the reason it is actually due to the physical damage that occurs. Like there's work being done and it's kind of internal to the system. They collide, they stick together, there's a deformation, there's some energy that's happening, some change in the energy into other forms. So there's two kind of terms, and one is an elastic collision, one is inelastic collision, and we'll talk about more about that in the next lesson. But essentially, in an elastic collision, kinetic energy is conserved. Inelastic collision, kinetic energy is not conserved. And so we'll talk about more about that a little bit later. So here's the big idea. If we make both objects part of the system, so let's say we have two blocks and they're going to collide, and we make it part of the system. We say, I want the system of two blocks. My system equals two blocks. Just like we did with work and energy, we define a system. Then any interaction between them coming together and hitting each other is internal to the system and is not part of the external impulse. When we think about this part here, this force is all the external forces. Just like when we did work, it's the external forces to the system. So the system is super important when we're defining it. And very often in a collision, we will define both objects to be part of the system because precisely we don't have to worry about what the interaction is doing. That's now internal to the system, and we just focus on everything outside of that. Okay, and so when we do conservation of momentum, by the way, is just like with work and change in energy. When was energy conserved? If this equaled 0, then we had conservation of energy. Similar thing to here, if this is 0, then then there's no change in momentum. And we call that conservation of momentum. So when is momentum conserved? Not always. Right? It depends on the system context. It depends on whether or not there are any external forces causing an impulse onto the system. So let's talk about the center of mass of a combined system. So how does this work? Like if two objects collide, right? We have two objects heading towards each other and they collide and we group it as a system. And let's say the external forces are 0. Then we say the change in momentum is 0. Right? The momentum is conserved. Then if there are no external forces, the center of mass of the system doesn't have any acceleration. Just like we did in kinematics before. We said the center of mass, if there are no external forces in our system, then there's no F net. Remember that F net equals ma. If this is 0, then this is 0. Right? However, so the center of mass won't change. This is the key thing. In this collision, we define this system. The center of mass of the system has no change in its momentum. That is, the velocity of the center of mass is not going to change. However, individually, the two blocks are going to have a change in momentum. And we'll go through an example to illustrate this. But this is a really, really, really key point. Each object may have a change in momentum because from its perspective, it is experiencing an outside impulse, like a force. Like if we talk about the system of this block here, he's going to get hit by this block, right? But if we talk about the system as a whole, then it's internal. So I want to reconcile that part. This part gets a little bit confusing to students, and so I want to make it very clear what the system is and when the momentum is changing and how exactly is it changing. So let's go through the problem-solving steps. Overall, you'll get a chance to practice it, but this is the main idea what we're going to do, and then we'll go through some examples. So first, we want to identify the system. When including both objects, if the force is internal to the system, it doesn't contribute to an external impulse. We draw a free body diagram of the objects. First two steps are very similar to our work in energy, right? So we're going to identify the system. We're going to draw a free body diagram. If there's an impulse acting on the system, there's a net force over time. So determine whether or not that's happening. I would say 90% of the time, there's not going to be an external impulse because it's the scenario is contrived in such a way that we're practicing conservation of momentum. So specific things. In a collision, the time of the collision is very short. We assume the impulse from the non-normal forces is negligible. So that means like frictional forces or tension forces, anything non-contact forces, non-normal forces, we assume are about 0. Gravitational force too. We assume that because the time is so short in the collision. Be very careful. Impulse is a vector, so there may be some impulse in the x direction, some in the y direction, or vice versa. Then we're going to calculate the impulse. we're going to calculate the initial momentum, the final momentum, and then apply this. Okay? So let's kind of like illustrate. Let's put it all together and go through an example, because I know it sounds very abstract. Let's go through some examples so you can kind of see what's happening here. So if two lumps of clay with masses m and 2m are traveling in opposite directions with speed 3v as shown above. The lumps of clay collide and they stick together. Okay, so these two are gonna, so this is before they collide, and then after they collide, they're gonna be one giant mass, right? There's the m and the 2m. They're stuck together, and they're gonna move with some unknown velocity v. We don't know what this is. What is the speed of the combined lump of the clay after the collision? So here's the whole idea of our system. In general, if you're not told, we're just gonna say, look, the system is going to be both objects, because I don't want to deal with the what forces that each block is experiencing on each other. So the system's going to be the two lumps of clay. That's step one in our process. Identify the system. Okay? Now we want to decide, we want to draw a free body diagram of our system here. So our system is this. Okay, and then let's draw gravity. Right? We have an mg. Or draw a free body diagram. I have a normal force here. If it's sliding on something, 2mg, and then a normal force. Assume no friction. I told you there's no friction. Let's just, or I didn't say there's no friction, but we're going to assume no friction. Okay, just because I made up this problem, so I get to change the rules on it. So in this case, no friction. So there's no horizontal forces. Okay, so in the x direction, right? They will experience a force on each other when they hit, but that's internal to our system. The x direction, the impulse is 0. And that implies that the change in momentum is 0. So let's do right is the positive direction. And now let's do the initial momentum. So the initial momentum is the total momentum of this system as a whole if we're assuming right is the positive direction. Remember, this is a vector. So we take the momentum of this guy, which is m times 3v, and then you have a 2m, this mass, and his momentum is 2m times negative 3v. Why negative 3v? Because it's going left, and left is the negative direction. Okay, because they're vectors, right? We've got to treat it like vectors. So this is 3mv minus 6mv, and that's negative 3mv. Now the final momentum, they're moving together with some unknown speed v. So we'll just say it's 3m times some final velocity here. And because there's no change in momentum, right, we're applying this process is equal to final momentum minus the initial momentum. So this is 0, final momentum minus the initial momentum, which this implies that the final momentum and the initial momentum are equal. And that's conservation of momentum. So then we say 3mv. Actually, sorry, let's give this a different letter. Let's call this vf. Okay, vf. 3mvf is equal to negative 3mv. So the vf then divided by the 3m's cancel, you get negative v. So overall, this is going to be going negative v, which means it's going to have a leftward direction because it's actually negative. I guessed wrong. It's not right. It's left. So it's a negative direction with speed v. So the speed is v here. What is the velocity of the center of mass before the collision? Okay, let's do that. Let's just verify this. So what is the velocity of center mass calculation, right? We're going to sum the velocity of the object times the mass of the object divided by the total mass, right? And so this is going to be m times 3v plus 2m times negative 3v. Oh, look at that. That's the momentum calculation. If you notice it, that's the momentum calculation we just did. Divided by m plus 2m, which is 3m. And that's going to give you 3mv minus 6mv, which is minus 3mv over 3m. And that's going to get negative v. Now, why did we get this? This is before the collision. Why did we get this? This is what I was saying before, is because there's no external force on the system, the center of mass velocity was negative v before the collision, and after the collision, the velocity of the center of mass is still negative v. So notice there was no change in the center of mass velocity in this collision. Okay, and that's an important thing to recognize, is that when you define this system, if you're talking about the center of mass, now, of course, individually, And this is the thing you got to recognize. Individually, the two pieces of clay obviously had changes in their velocity. Like this guy was going 3v, this guy was going 3v. Now they're not going 3v anymore. Of course, each individual block changes their momentum, changed their velocity. But the center of mass velocity didn't change. Okay? And that's the thing you're going to recognize. So what is the velocity center mass after the collision? Negative v, right? Didn't change. What is the change in momentum of each piece of clay? So now we want to think about what is, for the left clay, what is the change in momentum? So for the M1, his initial momentum was 3mv because he's m and 3v to the right. What is his final momentum now? Well, now he's, if you just think about just this guy by himself, the m is now going negative v direction, right? So it would be m times negative v, which is negative mv. So the change in momentum for the M block, the left clay block, is final minus initial. And so you get negative mv minus 3mv, which is negative 4mv. Okay? How about the 2M block? Well, his initial momentum was to the left. He was initially going 2m and 3v to the left, so it's 2m times negative 3v, which is negative 6mv. And his final momentum is the 2m is now going in the negative v direction, right? Because they're both moving. This block right here is moving to the left with v. So that's minus 2mv. And so what is his change, which is again is final minus initial? That's minus 2mv minus negative 6mv. And that gives us positive 4mv. Okay, and so what has this told us? What has this ultimately taught us? Is that couple of things. In a collision, if there are no external impulses, right, and the momentum is conserved, the velocity of the center of mass doesn't change and the momentum of the overall system doesn't change. However, each individual block does have a change in momentum, but they change in equal and opposite, so the overall change total is still zero. So this part gets a lot of students get this mixed up, is to say, like, when the momentum's conserved, it's like we're not saying individual pieces aren't changing. We're saying overall the center of mass of the system velocity isn't changing. Okay, when there's a collision occurring, if there's no impulse, no external impulse, then we're saying the overall center of mass velocity doesn't change. Each individual piece might change their momentum, but it's always going to be an equal and opposite amount because the total has to still be zero. If his not total isn't zero, then that means there was an external impulse that caused a change in that system. Okay? Let's do another example here. This is similar to the one before, but we're going to go a little bit deeper in this one here. So this first two parts we did in a previous lesson, but let's go through it again. And we'll just derive it in a slightly different way. So we have student, by using conservation of momentum in some cases. A student of mass ms standing on a smooth surface uses a stick to push so we have a student here. He's got a little stick here, right? And he has a mass ms, and he pushes a disc with mass md. Okay? So they're going to apply a force on each other, an FH this way, and then an equal and opposite force is going to act on the student, because when he pushes on the block or the puck pushes back on him, or disc. Derive an expression, so it applies a FH over a time interval from 0 to TF while pushing the disc. Assume there's negligible friction. Assuming the disc begins at rest, determine expression for the final speed. So we've done this before, but let's just go through it again. Our system is going to be just the disc. In this case, we're not going to put the student and the disc together. We're just going to talk about the disc. And so the impulse, which is the change in momentum, is going to be FH. He does it over the time period TF. And this is going to be his final momentum. So later this disc is moving VF. Or moving, VD. And this thing right now is velocity, initial velocity 0. So the change in momentum is going to be the mass of the disc. The final momentum is going to be, if we make right positive. Sorry, I hid that picture a little bit. Hopefully you can see that picture. So the right's positive, so that's VD, and then minus MD times 0. So you get the VD here is FHTF divided by MD. Okay? So that we did that before. That's impulse momentum part. Now let's talk about the student, and let's do a little bit differently. Before we did when we did this in the previous lesson, we said like, oh, well, we just have an impulse on the other guy. But let's think of it as a whole system. Let's think of this as like a collision a little bit. Okay? And if you think of this as the system, so our system being, because they're asking here, there's negligible friction between the student's shoes and the surface. After time tf, the student slides with speed vs. So he's going to move here with vs. Derive an equation for the ratio of vd to vs. Express your answer in terms of ms, md, and physical constants. So the system is going to be the student plus the disk. Oops. And then if we draw our free body diagram, we're going to notice we don't have any other horizontal forces because we have gravity, we have normal force, but there's no friction, right? So there's no horizontal forces. So in the x direction, remember, momentum's a vector, so we got to think about the x and the y direction separately. In the horizontal direction, the impulse is 0, which implies the overall change in momentum has to be 0. So now we look at the initial momentum. The initial momentum is 0 because they're both at rest. The final momentum is the md is moving at a velocity vd, and then the student is moving at a velocity negative vs. And because the change in momentum is 0, so that's the m times v, we said right was positive, this is m times v of this guy, then by conservation of momentum, we're saying there's no change in momentum, this has to be 0, so md vd is equal to ms vs, right, just moving it over. So then you see, if you solve for vd over vs, move the vs over here, and then move the md over here. So then you get it's equal to ms over md. If you look back on that previous lesson, we got the same thing, that first lesson on impulse momentum. Okay, now assume that the student's mass is greater than that of the disk. So ms is greater than md. On the grid below, sketch graphs of the speeds of both the student and the disk as a function of time between 0 and 2tf. Assume that neither the disk nor the student collides with anything after tf. On the vertical axis, labels vs and vd. So initially, they're both moving at 0. So let's do the disk first. So the disk is going to go up here, and we'll say this is vd. Okay, and then after that, the impulse goes away because now they're not pushing on each other anymore. So there's no horizontal forces. So then there's no acceleration. So the velocity is just going to continue straight on. Okay. Now let's talk about the student. Actually, the disk is going to move faster. So let's say vd is like over here. That's a straight line. So that's vd. This is vd. Why do I know that? Because the student's mass is greater. If ms is greater than md, then that means vd over vs is greater than 1. So vd is bigger than vs. Now let's talk about the student. What is he going to do? Is he's going to experience a force like this, and he'll have a vs here. And this will be vd. He's going to do the same thing because after they're not pushing on each other anymore, the acceleration 0. And remember, for a speed versus time graph, the slope's going to be the acceleration. Okay, so that would be vd and vs. Oh, and then label s. Oops, s is this guy down here, and d is this guy down up here, like that. Okay, let's do another one. We're doing conservation of momentum process. So first, we have a 2,000 kilogram freightway coast at 4 meters per second. So it's going 4 meters per second. Coast constant speed, the acceleration 0, right? Underneath a grain terminal, which dumps grain directly. So there's a grain terminal that's going to dump grain down into the cart. So the cart's now going to get grain dumped into it. And then eventually, it's going to be filled with grain. Now, the speed of the loaded freight car must not go below 3 meters per second. That means 3 meters per second is the slowest we can go. Now, why is it going to slow down? Well, the grain's going to hit it. It's going to apply some forces to cause it to slow down because it's just coasting, right? It's not like there's an engine pulling it the whole time. It's that it's here. But so there's a complicated interaction between what the grain does. It hits it, and it's going to apply a force this way. Each grain is going to hit the train and cause it to slow down. It's going to push it because the train's going to accelerate the grain to make it to go the same speed as the train or the freight car. And then the grain is going to then cause an equal and opposite force in there. But if we think of the system as the grain plus, so there's a complicated interaction between the grain and the cart as it hits. So if the system is the grain plus the car, then we don't have to worry about the internal forces of what's happening in between there, right? So then we're going to draw our free body diagram. We're going to say like, okay, so we definitely have gravity of the grain. We definitely have a normal force. But do we have any horizontal forces? We just talked about the grains they can exert, but assume there's no friction, right? It's just coasting along here. There's no horizontal forces. So again, in the x direction, F delta T is 0. Now, that's not to say, by the way, the vertical direction that these forces are equal, because clearly what's going to happen is the grains are falling down, has a momentum downward, and then they come to a stop, right? Because there's an upward force from the cart, and thus, so we're not necessarily saying in the y direction. I don't necessarily know that the impulse is 0, because I don't know the vertical the vertical center of mass and how that's changing. Okay, because this grain is falling, but horizontally we know there's no forces, right? We'll make right the positive direction, and so we'll look at the initial momentum of the system. The 2,000 kilogram cart is moving to the right, or so it is at 4 meters per second. The mass of the grain is falling vertically, right? The grain is dropping downward, dumps grain directly downward. So the velocity, it has a velocity, but it's pointing downward. But I'm only focused on the x direction right now. So there's no horizontal velocity because the velocity is only pointing down. So this would be 8,000. Now the final momentum, okay, is all of the grain in the cart, like it's all settled. It's all moving together at 3. So it's going to be 2,000 plus the mass of whatever the grain is moving at 3 meters per second to the right. Okay, which is 6,000 plus 3 mass of the grain. And we're going to set that equal to 8,000 because we said there's no impulse, so there's no change in momentum. So then you can solve for the mass of the grain. It's 2,000 divided by 3. What is that, like 667? Let me just double check. 667 kilograms, like that. Okay.